So pretty much what I want to do is make it so you can finish both the homework problems. So the first one's a little easier in a lot of ways, and then there's some things that are a little more complicated. So I'm not going to do the exact problem just because I don't want to like fully do your homework for you, but the basic setup is that we have some variables. So it's kind of similar to what we did before. We have like x1, x2, x3. And he specified that, so I'll keep with the fact that the expected value of xi is equal to 0. And then I'm going to change this a little bit. So I'm going to say the variance of x1 is equal to 1, the variance of x2 is equal to 2, and the variance of x3 is equal to 3. So in his problem, when he did it, I'll do in blue, he said all the variances were just 1, which doesn't change much, but it changed a little bit. And then I'm going to let the covariance between xi and xj just be equal to 0.25, or obviously this is if I does not equal j. So then he basically says, okay, you have some sort of matrix or some vector z, which again this is kind of what we did. So I'll just write it as this. So it's kind of like a linear combination of these. So we have z1 is equal to x1 plus x2 plus 1. Z2 is x2 minus x3. Z3 is just a constant 7. And so what he wants you to do first is find the covariance matrix. I'll do it over here. So A, he wants you to find the covariance matrix of Z. So I'll just do this really quickly because I think it's kind of review. So you just do the covariance of, and then you write the matrix times X basically. So as you can see, this is going to be 1, 1, 0, 0, 1, negative 1, 0, 0, 0, X plus 1, 0, 7. I'm actually going to write variance because it gets kind of murky because you have like the covariance matrix, but then the variance of it. And so I prefer to write variance. It just makes more sense to me for some reason, but it doesn't really matter. And then this is going to be equal to, as we've done before, basically this doesn't matter, right? Because it's a constant. So you can just ignore the constant and you just do 1, 1, 0, 0, 1, negative 1, 0, 0, 0. I'll write variance of X. And then the transpose. So 1, 0, 0, 0, no, 1, 0, 0, 1, 1, 0, 0, negative 1, 0. And then we have the variance of X from up here. Just this. So the variance of X down the diagonal is just going to be 1, 2, 3. And then it's going to be 0.25 everywhere else, right? Because the covariance between everything else is just 0.25. Okay. Times that. Down a little bit. So then I simplified this, so don't worry. So if you calculate that all out, you end up getting, kind of useless to do the math, 7 over 2, 7 over 4, 0, 7 over 4, 9 over 2, 0, 0, 0, 0. So this is the covariance of Z. Okay, and then the next thing they ask is, what is the correlation coefficient between Z1 and Z2? So when you're doing this in the homework, the variance of both of them is 1. So the covariance is going to equal to the correlation. Because remember, the correlation is equal to the covariance of Z1 over Z2 over the square root of the variance of Z1 times square root of variance of Z2. So it's just going to be 7 over 4, so that's the covariance, over the square root of 7 over 2 times the square root of 9 over 2. So make sure he wrote correlation coefficient, not the covariance coefficient. Those are two different things. And you can probably simplify this, but I'm not going to. That's that. So the next thing they want you to ask is they say, is this matrix up here covariance of Z, positive semi-definite. Okay, so there's a couple different ways to figure out if a matrix is positive semi-definite. I'm going to give my personal recommendation for an answer for this. Do either of you guys know a way to figure out if a matrix is positive semi-definite?
I could think of would be calculating all eigenvalues and then
Yes.
seeing if they're not negative.
Yeah, perfect. So what you want to do here is just calculate the eigenvalue. So yeah, calculate eigenvalues. So again, I did this for the one you do in your homework. It's a lot easier. Don't worry. I just pick random numbers and then they don't work out very well. But you just calculate the eigenvalues. Again, if you want me to go over anything like that, I can. I try to like not go over a lot of the boring calculation stuff. So when you do that for this matrix, the eigenvalues end up being lambda equals to 0, and then you get 8 plus square root of 13.25 over 2, and 8 minus square root of 13.25 over 2. And just FYI, this is a positive number because obviously this is less than 64. 13.25 is less than 64. So this is positive, and obviously this is 0. So we have positive semi-definite. But also just FYI, all variance. So is it? Yes. Also, all covariance matrices are positive semi-definite. They have to be. So you could have also, I don't know if you wanted you to check. I don't know if you've proven that yet, but they all are. And then he also says, okay, here's an interesting question. So he says, is it possible? So is there, so let's look at this. Is there an a non-zero A vector such that variance of A transpose Z is equal to 0. Okay. So if we think about this, so how I would do this is write this out as A variance of Z, A transpose variance of ZA. Now we have to find, is there a vector such that this equals to 0? Well, here's a question for you. Is there A such that variance of Z, the variance matrix of Z, which we calculate up here, times A is equal to 0? I won't give the answer. You can prove it from what I have above here. The other way of saying this is kernel of the variance of Z not equal to just the 0 vector. However you want to think about that. Does that make sense to everyone? That was pretty much question A and B for problem 2.1. Let me know if you have any questions. Okay. So then I think C and D are also pretty easy. So they ask you to find, so C is just find the variance of Z1 minus Z2. So I think you can all do that. Just rewrite it as you did with the X's basically. D says find, okay, so D, I want to just note something. It says it says basically like, let Y equal a constant. So I'll just say 3Z plus 1, 2, 3. And it defines this as 3Z1 plus 1, 3Z2 plus 2, and then 3Z3 plus 3. So note that you cannot just take 3 and multiply it by the variance thing, or even square it, which might seem like you wanted something else to do. That might seem like it's easy because, right, you're thinking like, oh, variance of 3Z, just pull out the 3, you get 9. Well, it's not exactly how it works. Actually, yeah, I don't think so. Remember, this is, so rewrite this in terms of something, I'll say B times Z1, Z2, Z3 plus obviously 1, 2, 3, and then go from there. So don't trick yourself up on that one. Okay, so the first one's pretty much mostly review. Again, the only tricky parts really, I think, would be, the part about positive semi-definite is, I think B is a little bit tricky. But then C, D, and A are all things you should have seen before. Or if you haven't, you've now seen it again. Okay. So any questions about, do you guys think you can do 2.1 now?
Yeah, I definitely think
Yeah.
so.
Lit. That's my job. Okay, let's do question 2. So again, this one's gonna be a little bit, so I just want to go over some things that you should see. So it's again, it's all linear algebra review, but it's like a couple things are a little tricky. So I'll try to give you some hints. So in this case, we have so problem 2.2. We basically have that p is less than or equal to n, and we're letting x be an Rn by p, and we're saying it's a full rank matrix. Okay. This will not complicate things. It might just make it so that I'm saying, but I'm just gonna let this, this isn't in the problem, but I'm gonna let p equals n and let x be an Rn by n just to make some of what I'm saying easier. So I don't have to remember if I'm doing columns or rows or whatever. But maybe when you're writing it, for the rest of this, I'm gonna say n all the time, but some of these might be p, just as a warning. Like it might actually be, but I'm just gonna let p equals n just to make it easier to explain stuff. Because I always get tripped up with transposes and blah, blah, blah. Okay, so this is all about H matrix, which is called the hat matrix, and it's equal to X transpose, X inverse, X transpose. So for A, they just ask you to show that H transpose is equal to H, and then H squared is equal to H. So I'm not going to do that, but it should be pretty easy. Just literally write it in terms of the X's and then go from there. The next one is for B, it asks you to prove that, it asks you to let V equal to the image of X. Okay. So
For A,
yeah.
is that the exact same problem for homework?
Oh, did you have to prove that as well?
I
Oh
thought we did,
yeah,
but I don't know.
I
It
think so.
looks really
Yeah,
familiar.
I think so. Yeah, yeah, I think it is the
Oh,
same.
okay.
Yeah, you're right. So you already have it. I'm gonna say. Oh, okay. So it asks you to find. So it wants you to let V equal the image of X. So the question is, basically, it just wants you to show that for Y in Rn, Hy is in V. Okay. So let's break down what this means, really, right? Let's look at the image of X, which is V. So I want to be able to write, so the image of X, right, is equal to basically, so I'm trying to think if this is only the case when it's full rank. Well, okay, so the image of X is equal to the span of the linearly independent columns of X, right? That's something we've done before. But remember, this is X is full rank. So I don't know if this is fully necessary to include. You kind of can just skip, I think, to the end of this. But remember, the reason this works is that X is full rank. So it means that this is equal to the span of the columns of X. So all of them are linearly independent. And so I can rewrite the image of X as basically anything that looks like this. So it's going to be like anything that looks like this, C1, X1. So if I let X, put it up here. If I let X equal X1 column, X2 column, Xn column, then the image of X is anything that looks like this, C1, X1 plus C2, X2 plus Cn, Xn. But this is also equivalent to saying basically X, the matrix X times a vector C, right? Where C is equal to C1 through Cn. So this is something that might trip you. So again, you might be like, oh, this is really obvious, but in case it trips anyone up, V, which is equal to the image of X, can be written as anything of the form X, I'll say V, no, that's a bad one, U, such that U is just a vector. And again, I'm letting everything be an Rn. So it might actually be Rp if you do it. I'm too lazy to check. So anything that be written as X times a vector is in the image of X, okay? So to prove that, so if we want to look at Hy, this is equal to X transpose X inverse X transpose Y. So see if you can make this look like this in some way for some u. And then that will prove that hy is in the image of z, or the image of x, which is equal to v. Okay. Cool. Yeah. The next one asks you to find that it says e, which is consider the error vector, is equal to y minus hy, or also written as I minus hy. Okay. And it wants you to show that E is in the orthogonal complement of V, which he basically says, okay, just use the fact that this is equal to the kernel of X transpose. So remember, if something is in the kernel of X transpose, what we need to basically show is that, so we need to show that X transpose times E is equal to 0. That would be the same as saying that E is in the kernel of X transpose. So again, just rewrite this as X transpose times I minus X transpose X inverse, X transpose Y, and just try to make this go from here and simplify this to see if you can make it equal 0. And then he says this, he basically says that B and C show that HY is a projection of Y onto V. So let me kind of explain that just to visualize what's going on and why this proves that. So remember we proved that for any Y in Rn, HY is in V, and then we showed that I minus HY E, which is equal to I minus HY, is in the orthogonal complement of V. So if we visualize this, what we end up getting is that if this is V, okay, we said that Y is this. So Y is any vector, right? We said that HY is in V. So I'm going to draw HY in red. HY is in red. This is HY. And now we don't exactly know much about HY right now. We don't know if it looks like that. We don't know if it looks like that, or that. It could look like anything, right? We don't actually know. So it could look like this, could look like that. All we know is that it's somewhere in V, right? We don't technically yet know anything else about it. But then we have the fact that I minus HY, which is, so Y minus HY up here, right, is orthogonal to V, okay? So Y minus HY is the difference between Y and H, obviously. So if it's orthogonal, that means that when I go from Y to HY, I should be going down vertically. This needs to make a right angle, right? So if HY is, so this is E, which is equal to Y minus HY. So if HY is in V, as we said, and then E, which is Y minus HY, is orthogonal to it, those two facts together show that HY is the orthogonal, is the projection of Y onto V. And so when you're doing regression, Y is your data. Obviously, it's probably something explained, but Y is your data, HY is your estimate, basically, and V is the space of linear combinations of the Y values. Is that right? No, that's not right. It's V. Image of X. Oh yeah, okay, sorry. So V is the linear combination of data vectors. Sorry about that. So basically you're saying, okay, if I want to take a linear combination of the data vectors, which is what I'm trying to do with linear regression, right? Because remember, linear regression, you want it to be a linear combination. So you need, it's based, so a linear combination naturally corresponds to a linear regression represented as a linear combination of something naturally corresponds to a subspace within Rn. Therefore, if we have any data vector, the best we can do within the linear combination of, if we have any resulting vector y, the best we can do within the linear combination of data vectors is going to be hy. And the best, for the best error, which will be an orthogonal error, is we can do is e. Okay. The next thing is, it says show also that, and I think you guys did this, that I minus 8, I minus h transpose is equal to I minus h, and then also show that I minus h squared is equal to I minus h, and I think you guys did this last homework as well. So just look at the last homework. The next thing it asks is, and it's weird because he asks it, but I'm not sure if he wants you to answer it or not, but it says, can you guess what subspace it projects onto? So can you guess what subspace I minus h projects vectors onto? Well, actually, it's quite easy. If you'll notice, so remember E, which was equal to y minus hy, or also equal to I minus hy, is orthogonal, right, to V. So this is orthogonal to V. So again, this is not a formal proof of this, but I guess you prove this in C, basically, that I minus h times of any vector is going to be in the orthogonal complement of V, and that's quite obvious from this picture as well, right? E is a projection of y onto the orthogonal complement of V. So you project y onto, and which makes sense, right? Because it's kind of like the orthogonal thing of h would be I minus h, like it kind of makes sense, right? But yeah, if you project y onto V, then I minus h is going to project y onto the orthogonal complement of V. So it's going to go down this way and it's going to go that way with I minus h. Okay. I'm going to give you that one because I don't know if that was an actual question or if he was just, I don't know if he was like, can you guess? And you're just like, no, I can't guess. Is that a fair response? I would say that. Sometimes I do that. Sometimes in like grad classes, they like don't care if you like actually answer the question. They'll be like, oh, like it's fine. You don't have to do that homework. My roommate's a math PhD and he always says that like it takes like about like it takes like if you know if a homework problem takes like 100 or homework assignment takes like 100% effort to complete, right? Like the first like half of it, or not even that, the first like two-thirds of it takes like out of that 100 effort, maybe like 40% of the effort. Like it takes such a little amount, and then to get like the last like most of the last third takes like the other about 60% or another like 40%, and then takes like 20% more just to get like the very last ones. And he's always like, so I just don't do the hardest ones. I just don't do it. And I'm like, you know what? I gotta respect you, man. I mean, he did graduate, so okay. Anyway, don't do that for undergrad though. It's a very bad idea. Unless you want to go to grad school. No one ever wants to go to grad school though. Except for me. Okay. So basically, then E says that H is symmetric. So H can be written as decomposed into U lambda U transpose. So the reason that it can do this is H is symmetric. If H was not symmetric, in case you're curious, you could write this as U this and then V transpose, I believe. Don't quote me on that. I think that's right though. Actually, that'd be wrong. Oh, there's too many matrix decompositions. This is always my worst thing. Anyway, so basically it's yes, you can write it like this. And remember, U is what is the word for it again? Orthogonal. So when you use orthogonal, that actually means that, remember that, or the orthogonal matrix means that U transpose is equal to U inverse. That's what orthogonal means, in case you've forgotten. And then it basically says you want to prove that, and then lambda is diagonal. So lambda is actually the, remember, it's the diagonal matrix of eigenvalues. Okay. And they want you to show lambda squared is equal to lambda. So just, I won't do this, but obviously you can say that h squared is equal to h, and it should be a very natural progression from this to this, if you remember this fact. So just, this is the key part. And this, you know, those two things, you should be able to get it very quickly. And then it says, what does this tell you about the eigenvalues? So if lambda squared is equal to lambda, it says, okay, what does it say about the eigenvalues? So again, I'm not going to exactly say, but in case you've forgotten, again, I don't know how much matrix calculus y'all have been doing recently. I know when I came here and I had to do matrix algebra, I did terrible. But then I got through it. Remember that if you have basically lambda 1 through lambda n squared, and it's a diagonal matrix, these are zeros, you'll just square the diagonal. It's as simple as that. So then go from there. And I think that will reveal what that says about the eigenvalues quite easily, because then if this is equal to lambda 1, lambda n, you'll see some stuff. Okay. So any questions about anything I'm doing over?
I don't have any questions. I'm a little bit lost, but I think it'll make more sense.
Oh God, you're lost? No, wait, I thought it would be clear. What are you lost about?
No, I think you are. I think just when if I were to do it myself with the video help, I think I could do it. But
okay. This is for reference. Okay, it will be up tonight. It takes longer for me to upload these on YouTube than it does for me to upload on CCLE, but it will be up tonight. So it's for you to watch.
I appreciate it.
Okay. Is it like all the matrix stuff I'm doing? Am I going too quick with that?
I mean, maybe. I don't really know.
Okay.
I don't know.
Let me know if you have any questions.
I don't know if you're.
Yeah,
I
what's
think
up?
you're too quick. I just think it's hard because I haven't looked at this problem yet.
Okay.
Like I haven't tried it myself, so then
okay.
I'm not quite sure yet. But I think you're actually explaining it very well. I'm just
okay.
haven't done it yet.
Okay. So this will be helpful at a later point, or when you look at it more deeply. Come back to this. People watching at home, come back to this. Okay. Let me try to write the problem a little more clear. Okay, so let's look at F. So yeah, again, this is a lot of like linear algebra stuff. So again, I'll give you some hits for F. So for F, you have that. So again, they're saying that they're letting y hat equal hy. Okay. That's just a notation. And then they're saying that E is equal to I minus hy. Okay. And they want you to prove a couple things. So the first thing you want to show is that they want you to prove that the L2 norm of y squared is equal to the L2 norm of y hat squared plus the L2 norm, no, sorry, not this, squared on the outside, sorry, plus L2 norm of E squared. So whenever you see this, so there are a lot of norms. So in general, when you see this, assume it's the L2 norm. Technically, you could also write this with a little 2, but typically people only write this if it's not the L2 norm. So there are other norms, like there's the L1 norm, which people usually write like that. Or people just more in general write this as like the LP norm. But in general, if you don't see a letter there or a number there, sorry, just assume, or a number or letter, assume it's the L2 norm. So to be clear here, y can be written as, so if this isn't clear, so y, all right, the L2 norm of y, can be written as y hat plus E. And so if you haven't seen that before, the reason for that is basically if you say, if we write out what y hat plus e is, which is hy plus I minus hy, or AKA hy plus y minus hy, it's just equal to y. So you can just replace this with this, squared, obviously. And then from here, remember, this is not equal to just this. You can't just break it up. But what you can do is say this is equal to y hat squared plus e squared. And then this is going to be plus, is it plus or is it minus? I don't remember. I think it's plus. Yeah, it's plus when it's, yes, plus 2. And then, again, it depends. I guess I'll write it. I think this is how we write it in class. So this would be the, what do you call it? The, oh my God. I'm literally blanking on the name for this. Inner product, that's it. The inner product of, so it's plus 2 times the inner product of y hat and e. And to make it even more clear, I really don't like this notation. I really prefer to write it like this. So this is equal to, y squared, y hat squared plus e squared plus 2, and then I prefer to write it like this, y hat transpose e. And so really what you just need to show is that y hat transpose e is equal to 0. A fun fact about this, so I would prove this mathematically, but let's look at, and again, you can just replace, I cannot write mathematically, I have no idea to spell this. So prove this formally, I would say, but, and you can just replace y hat e with what they are, you know, h and hy and I minus hy, and, you know, use the properties of h you have. But something to note is that this is pretty obvious because remember, we just proved up here that e and hy and e are orthogonal. And so orthogonal vectors automatically have an inner product of 0. That's the definition of orthogonal, is their inner product is 0. So it's going to be, it's quite obvious, right? That hy, aka y hat, and e are going to be orthogonal, aka have an inner product of 0. But you should probably prove this with the matrices because it'll probably be more illuminating. But you also could say that. You also could say like, oh, maybe after you do that, be like, oh, they're orthogonal clearly. Or maybe you just say, I don't know. You could probably go through a formal, a sufficient proof by like saying they're orthogonal since we've already kind of proven it. The next thing is for G, it says you want to show that L2 norm of hy squared is equal to y transpose hy. Now remember, this is going to be the L2 norm squared is going to be hy transpose times hy. So that's what the L2 norm squared is. The L2 norm is the same as the L2 norm squared of a vector is of just, one vector is just the same as the inner product squared. So this is equal to that. And then you want to just kind of, again, use properties of H. It's not very complicated. And the next question it asks is H positive semi-definite? Okay. Well, you can actually prove that before. So with this fact, you can prove that. So notice that this is to prove, so something to show that something is positive and definite, we need to show, right, that y transpose hy is greater than or equal to 0 for all y, right? Well, if it's equal to a squared term, right? So usually you would go through and find the eigenvalues, right? That's usually probably the easiest way to do it. But obviously we don't even have what h is, but you'll notice it's equal to a squared term. So that should be really obvious as to what the answer should be. That's that one. So then the next one They give you two matrices and they ask you to find the images of them. Basically, they give a matrix x1 and x2, and they say prove image of x1 is equal to image of x2. Again, this is not very exciting, but you can just literally just find them. Find image of x1 and image of x2, and then kind of show that they're equal. It shouldn't be too complicated. There probably is a better way to do that, but well, actually, no, it says that. So it says already that it says here. So it kind of gives you that the image of x1 is equal to the image of x2, but you also can kind of prove it if you want. The next thing they want you to do is prove, so verify H1, which is defined as x1 transpose x1 inverse x1 is equal to H2, which is equal to x2 transpose x2 inverse x2. You can do that a couple ways. You can just do it by hand, or you can kind of, I think that would be the best way to do it, honestly. Can't think of a better way to do it. I'm sure there is if you can think of one. If you can think of a better way, but also you can just, if you want to, just literally multiply them out and see what happens. And then finally, I is just saying that find projection of a vector y onto image of x, calculate E. Again, this can just be done by hand. E squared, you'll see when you get there about what happens, but again, you can just calculate it, based off linear algebra formulas, see what happens. I won't reveal exactly what happens, but it will be quite obvious what's going on. You get it. Okay. I think that is the entirety of the homework. Hopefully this will save you some time. Do you have any questions about anything? Want me to go over anything again?
I think that'll all make sense later.
Okay. Yeah, let me stop recording.